Hi everyone, in this video we're talking about section 1.6 from your text. So in section 1.6 we're talking about the placebo effect and some new vocabulary words and a few methods to design your experiments, types of experiment design. Now I'm just going to read you this little passage, and it's from something that was written long ago, back in 1813. But this says, we know that in Paris, fashion imposes its dictates on medicine just as it does with everything else. Well, at one time, pyramidal elm bark had a great reputation. It was taken as a powder, as an extract, as an elixir, even in baths. It was good for the nerves, the chest, the stomach. What can I say? It was a true panacea. So panacea means like a medicine for everything, or a cure-all. And if someone's trying to sell you a cure-all, something that could cure all of your ailments, that's probably what we call snake oil, right? It's probably not actually effective. It's probably a scam. But like we said, this is fashion, what's fashionable at the time, and we're talking about it being a fad. So he writes, at the peak of the fad, one of this doctor's patients asked him if it might not be a good idea to take some. And in response to his patient, this doctor says, take it, and please hurry up while it still cures. Which is to say, that this medicine, pyramidal elm bark, is really just a fad. And people are obsessed with it for the time being, and yet, since it's really not effective, eventually over time we're going to forget about it. And, people will be a little bit less fanatical about it. And of course, here in 2022, nobody uses pyramidal elm bark to treat anything. And so we recognize that it never really cured anything. But somehow, back in the day, way back in the day, sometime in the 1780s, people really believed that elm bark cured almost everything, right? They believed it cured nerves, it cured your chest, it cured your stomach, cured anything they could think of. And so why would people believe that something like elm bark could cure anything if it were really ineffective? This is what we call a placebo. So a placebo is the absence of a treatment where the subject or the individual taking the medicine is not really aware that the medicine is ineffective, right? And so we also call placebos sugar pills sometimes, just, in reference to like, if I handed you a pill and I told you that it was medicine that could really treat your disease, but the pill was actually just, a cake of sugar, and you take the pill and, you start to feel better. It's what we call the placebo effect, is when you believe that you are being treated for your condition. Sometimes that belief that you're being treated can actually make you feel better. It's just a psychological phenomenon. And I put a big tub of something called Blue Emu on the slide because people in my family use this. So actually for a long time, I don't know if she still does, but my grandmother loves this stuff. Again, who knows if she still does, but I do have memories of like 10 or 15 years ago, my grandma just applying this liberally anytime there was any kind of joint aches or headaches or anything, right? And the idea is that this is some kind of lotion that contains emu oil, and the emu oil is supposed to be pain relief. Well, honestly, I personally don't think that emu oil does very much, right? Like I don't think that rubbing emu oil on your skin is going to relieve joint aches or relieve headaches. But if you believe that emu oil is going to help you, then I think the placebo effect could legitimately relieve your pain, right? So if you believe that this lotion will relieve your pain, it might just make you feel as if your pain has gone away. This is the placebo effect. And sort of related to this concept, I want to mention something that people often state and often misunderstand, but it's a concept called regression to the mean. If you hear regression to the mean, see if the person using the phrase actually fully understands what's going on. So let's talk about regression to the mean. And we're just going to roll one die, so like one 6-sided die, and I put, sides of the die here, but remember dice are cubes, and so they have 6 sides, and they're labeled like 1, 2, 3, and so on, so that, all of these are faces of a die. If I roll a 5, right, and all of my possibilities are 1, 2, 3, 4, 5, and 6, and I roll a 5, what would be the probability that my next roll is higher? Well, higher than a 5, the only option for me is a 6. So 1 out of the 6 possibilities is going to be a higher roll. So the probability is 1/6. My next question is, what is the probability that my next roll will be lower? And if I've rolled a 5, I could roll 1, 2, 3, and 4. In other words, 4 possibilities out of 6 and get a lower result on my next roll. Okay, different situation. Now I'm going to roll one die, and I roll a 2 this time. Now the probability that I roll higher could be a 3, 4, 5, or 6. So 4/6. And if I were to try to roll lower than my 2 on my next roll, the only way I can do that is if I roll a 1. So I have a 1/6 probability of actually rolling lower than a 2. By the way, if I were to continue to roll this dice over and over and over and over, what I would expect to be the mean, or the expected value of rolling a 6-sided die, is going to be 3.5. Right? If I average 1, 2, 3, 4, 5, and 6 together, I expect to get about 3.5. And so what I want to point out here, anytime I roll a 4, 5, or 6, there's actually a better probability that on the next roll of the die, I'm going to roll a lower number than I did previously. And if I roll a 1, 2, or 3 on the die, then the probability is actually better that my next roll is going to be higher in value than my previous roll. So this is an example of regression to the mean. And I just, by the way, a new slide here, I went ahead and used a random number generator to just randomly generate some data points, right? So the mean of all this data is actually 0. So if you take all of these little dots all over the place, it's 0. And I put these random numbers in a particular order. So imagine this is a process, kind of a random process that's happening over time. And so time is going this way, and my random process is just generating different data over time. Well, even though all of this data is just completely randomly generated, if I do a little bit of an analysis here, and I let my y-axis, or my vertical axis, be the change in value from one data point to the next, and I let my horizontal axis, my x-axis, be the previous value, what this is showing you here is that whenever I get a particularly low value for my data, like if I get like -2 or something like this, actually it appears that the most probable outcome is that my next random data point is going to be considerably higher because I have a positive change for low values, right? A positive change as I go to the next value. And if I have a really high value randomly generated from my random process, I will likely have a negative change as I go on to my next value. And just to summarize this idea, whenever we have a random process and it generates one of the more extreme events, like it generates an unusually high number or an unusually low number, it's actually likely that the next outcome will be closer to the mean, because in reality, it's always been likely that the next outcome will be closer to the mean. One really practical application of this is if you watch baseball players, you look at baseball players' statistics, they might keep track of their home runs per season. And I'll be honest with you, I don't watch a lot of baseball, and so I don't really know what's a reasonable number of home runs per season. But let's say that 30 is a good number for home runs. And so a baseball player gets 30 home runs in one season. The next season, he gets 20 home runs. The next season, he gets 27 home runs, and so on. So he's let's say, an average to good baseball player. And then one season, you see the baseball player get just a phenomenal season. Like, he just does really great. He hits like 50 home runs in the season. Well, a lot of people, when they ask and speculate about what's going to happen in the following season, a lot of people think to themselves, well, since he got 50 home runs in the previous season, this means that he's doing better. Like, he's at the top of his game. He may be, the best baseball player in the league. I suspect that he's going to get 55 home runs in the next season, right? People expect really great results if they saw great results in the previous year. But actually, the probability is very, very high that he's going to get a relatively low number of runs, maybe 31 runs or something like this. Just because the probability has always been that he's going to score any number of runs in a season that's close to the mean number of runs over all of his seasons, and this is what we would just call an outlier. So, you might say lightning doesn't always strike twice in the same spot. Okay, so new vocabulary. An experiment is a study in which you purposefully influence the result in a controlled way. An experimental unit is one item that receives a treatment and is subsequently measured. When an experimental unit is a person, we call him or her a subject. So whenever we're actually dealing with people, like in maybe medical drug testing or psychology studies, we call our experimental units subjects if they're actually people. There are, experiments that involve not people, right? And so if you're maybe doing drug trials on mice, then we call those mice experimental units. But if we're doing drug trials on people, we call those people subjects. Okay. People get a little bit more dignity than animals do in this case, or plants, or whatever you're dealing with as an experimental unit. Okay, more vocabulary. We have a factor. So a factor is an explanatory variable, which is something that might affect the measured response variable. A treatment is a combination of factors intentionally applied to an experimental unit. A response variable is going to be something we measure, so something you want to see a change in. And a control group is a group that receives a placebo, or no treatment at all, in other words. So a factor might actually be like presence of a new experimental drug, right? So if you are trying to study whether or not one drug or another is safe and effective, you give all of your experimental units, half of your experimental units, an experimental drug to see if it's effective. That would be like a factor. It's the presence of the drug. The response variable, again, these are the same here. The response variable, if you are trying like a drug for seasonal allergies, this response variable might be like the severity of allergies, right? So we hope that our experimental drug might affect the severity of seasonal allergies. Okay. And by the way, for any drug trial, you always have a control group. So you have a group of people or a group of mice or whatever you're dealing with that receives a placebo. So they think maybe they're receiving the new experimental drug, but they're actually not. And we do this so that we can compare the severity of the allergies from the experimental group, who actually received the treatment, with the group who received a placebo. And we see if there's a difference in severity of allergies between the two groups. Now, a single-blind experiment is one where the subject is unaware of the treatment group to which they belong, right? So that's probably the best way to do it. You want to give, if you're doing a drug trial, it's nice to give people a placebo to make sure that they don't actually know whether or not they belong to the group that's receiving the experimental drug. And the reason we give, the control group a placebo is because, even if a drug is not effective, if you give the experimental group a pill that contains a drug, like I said, that's not even effective, and you give the control group nothing at all, well, the experimental group actually might believe that what they're receiving is effective when it's not. But even just the belief that you're receiving something effective can cause a change in the way that you perceive your ailment, right? So you might perceive that your pain has gone away or perceive that your allergies have gone away, when in fact you're just receiving a sugar pill or something that's not medically effective. Okay, so that's what it means to be single-blind, is just that the subject is unaware. A double-blind experiment is one where both the subject and the agent applying treatments are unaware. And so this is actually the gold standard in pharmaceutical trials. So in a double-blind experiment, you might have people distributing pills to the subjects, and the people distributing the pills don't even know whether the subjects they're bringing pills to are actually getting the placebo or just getting the real treatment, actually receiving the new experimental drug. And this can be important because the people delivering the pills, maybe they are doctors, and maybe the patients or the subjects in the trial can pick up on facial cues or just, the unconscious ways that we communicate with each other. Maybe one example is if an experimental drug is if we suspect that the experimental drug may have some side effects like, let's say, dry mouth or insomnia or something like this. And if you have only a single-blind experiment, then in a single-blind experiment, the doctor may ask the patient who has been receiving the real experimental drug, they may ask, are you experiencing dry mouth? Are you experiencing insomnia? And when the doctor is actually asking the subject these questions, the subject thinks, I might be really receiving the treatment or the new drug. Whereas the same doctor in a single-blind experiment might have another patient who he knows is receiving the placebo, and to this patient, the doctor just, doesn't say anything at all. Like, he's not actually concerned about this subject having any sort of side effects because he knows the subject is just getting a sugar pill. And so the subject might say, hey, this doctor is really not concerned about any side effects. I might be getting the placebo, right? And so there's ways that in a single-blind experiment, you might be worried about the subjects becoming aware about whether they're in the experimental group or the control group. Whereas with a double-blind experiment, if the doctors are unaware of which of their patients are actually in the experimental group or control group, then the doctors should behave the same towards all of their patients and ask them the same questions about possible side effects and have the same facial expressions as they go through the little procedure and distribute the pills. And so there should be absolutely no way that the placebo effect would play a factor or invalidate the results of the experiment. And so this is why we say a double-blind experiment is the gold standard. All right, so new vocabulary, a confounding variable. We have actually spoken about confounding variables, I think, in a previous lesson, but we'll bring it up again because it's pretty important. Confounding variable is a variable that is difficult or impossible to separate from the variable that we want to study, but might also have the same effect. But a well-designed experiment should separate confounding variables. So, at a university, an experiment was conducted to see whether a reverse classroom is more effective than a traditional classroom. And just as a note to you guys who aren't up on the lingo here, a reverse classroom is one where lectures are given on pre-recorded online videos, and the students are supposed to watch the online videos in between class. And when the students actually come to the in-person class, homework is completed during class. In a traditional classroom, normally you have the lecture happen whenever the students meet in person with the professor, and homework is done when the students are at home by themselves, working independently or with a study group, right? So you just flip-flop the roles of the classroom whenever you go from a traditional classroom to a reverse classroom. But I want to draw attention to this experiment here. So the experiment was conducted to see whether the reverse classroom is more effective than a traditional classroom. Now, an experimental unit for this reverse classroom experiment, I'll let you think about that for a moment. But the experimental unit would be a student. And so we would actually call these experimental units subjects because they're actually people. The factor or the treatment here is going to be whether the student is assigned to the traditional classroom or whether the student is actually assigned to the reverse classroom, right? So the traditional classroom we might think of as the control group because most classes are taught in the traditional sense. And the reverse classroom, we might talk about that as being the experimental group. So they're actually receiving the new factor that we want to try out. This is this reverse classroom. The response variable, so what we're trying to measure here to determine the effectiveness of each classroom type, the response variable is going to be probably student scores on a standardized test. So at the end of the semester, standardized test. At the end of the semester, both the students in the traditional classroom and in the reverse classroom are going to take the same final exam, and we'll see which classroom has better student scores overall to determine if there is a difference and if the reverse classroom can actually be more effective as a teaching method than a traditional classroom. The control group, I think I already explained this, so the control group is going to be the traditional classroom. Is there any blinding? And in this case, no. That would be impossible to do any blinding, right? So even just a single blind experiment requires the subject to be unaware of whether they are assigned to the control group or experimental group. And it would be impossible to have the students be unaware of whether they were assigned to a traditional classroom or reverse classroom, right? Just by nature of the experiment. What are some possible confounding variables? So as far as a confounding variable goes, I can think of one, which is the student and their intelligence, their motivation, maybe. And these are kind of, floofy things that we talk about, but we can't really measure intelligence that well, and we can't really measure motivation. But things you could measure that might be a proxy for intelligence and motivation might be the history of the student's grade point average, for example, or standardized test scores or something like this. And I say this is a possible confounding variable because if you ran this experiment and if you assigned the best performing students to the reverse classroom, maybe they're honor students or something like this, and they were assigned to the reverse classroom. And if you assigned students who had a history of, failing classes and having a low overall GPA, if you assigned those students to the traditional classroom, then you could actually expect that this is really going to affect your results, right? It'll affect your results in that you would expect the students who perform higher to perform better on that standardized test. So in this case, you wouldn't really be testing the traditional versus reverse classroom. You'd really just be testing, do honor students perform better than the students who are identified as struggling, And so that would be a bad way to do it, basically, is if you were going to run this experiment, you would not want to assign just the honor students to one of the classroom types and just the other students to the other classroom type. You would actually want to find a way to have the, maybe the historical GPAs of the students have the same distribution in both the experimental group and control group. That way you can separate out what we would call the confounding variable. So two good ways of doing this. These are both good ways of doing this, either a completely randomized design or a matched pairs design. In a completely randomized design, you could maybe sort the students into a list alphabetically and then use a random number generator to assign students to classrooms. And so this alphabetical list is what we would call a frame of all of the students that belong to our sample. And then again, the random number generator is going to assign students to either the traditional type of classroom or the reverse classroom. And the fact that we're using a random number generator should make it so that there would only be a very low probability that one of the classrooms is stacked with honor students, right? Another good way to do it would be called a matched pairs design. And in fact, not only is this good, but if you really want to control for that confounding variable, I would say that this is better. And the way that you would control for the variable of like IQ, this would be control for IQ as a confounding variable. The way we try to separate out that confounding variable is we're going to test the IQ of all the students in our sample who are belonging to the experiment. Then we sort the students by IQ. We're going to pair students of similar IQ. So we have one student with the best IQ, someone with the second best IQ, someone with the third, fourth, fifth, and sixth IQ. And what we do is we pair up first and second because they have the most similar IQ. We pair up third and fourth. We pair up fifth and sixth. And we're pairing up these students who have the most similar IQ to each other. And then we're going to intentionally split up these pairs. So this guy is going to go to the traditional classroom, and this guy is going to go to the traditional classroom, and this guy will go to the traditional classroom, and this guy will go to the traditional classroom, and this guy will go to the reverse classroom, and this guy will go to the reverse classroom, and this guy will go to the reverse classroom, and this guy will go to the reverse classroom, and so on. So the idea is that once you have these students separated into traditional classroom and reverse classroom, these classrooms will have roughly the same distribution of intelligence quotient, right? So you have students who are intelligent in both classrooms, and you have students that are average in both classrooms, and you have students who have a slightly lower IQ belonging to both classrooms. And that way you can make sure that IQ, at least, is not a confounding variable for your experiment. Now, it's been hypothesized that these two chemicals, which are caffeine and another one called L-theanine, it's been hypothesized that these two chemicals work together to improve student performance. So green tea contains both caffeine and L-theanine, and people hypothesize that the sum is greater than the parts. In other words, if you had some way of measuring the boost in performance, our expectation here is that if you added nothing to your normal morning routine, you would have no boost in performance over your usual performance. If you drank caffeine or this chemical L-theanine, you would have some boost in performance. But they suspect that if you had both caffeine and L-theanine, like you would if you drank green tea, they hypothesize that actually the combination of the two would be a much better boost in performance than if you just had one or the other, right? So that's what we mean by the sum is greater than the parts. And this is just to let you know, I don't know that this is necessarily what they found in the study, but this is our hypothesis. So if you were going to conduct this experiment, you would have to separate all of your participants, all of your subjects, into these 4 different groups. So group 1, we might call it our control group because they're going to receive no L-theanine and no caffeine. Group 2 is going to receive no caffeine, but they will receive L-theanine. Our third group is going to receive caffeine, but definitely no L-theanine. And then our fourth group is going to receive caffeine and L-theanine. And so again, to remind you of our hypothesis, we hypothesize that group 4 is going to perform much, much better than group 2 or group 3. And we again have group 1 as a place to compare to as just a control group. Now, I want to point out that having the presence of L-theanine, that's what we would call a factor. We expect that the presence of L-theanine is going to have an influence on the results. And caffeine, we call it a factor because, again, we expect it to have an influence on our response variable, which would be student performance. Now, each of these groups represents what we call a treatment. So having a placebo is a treatment. Having just L-theanine but no caffeine is its own individual treatment. Having caffeine but no L-theanine is also a treatment. And having both is also its own unique treatment. So in this experiment, there is actually 4 unique treatments, and there is in this experiment 2 factors at play here. So by changing whether or not they receive each of the 2 factors, we can generate 4 unique treatments in this experiment. This is the difference between the word factor and the word treatment. They kind of mean the same thing, but not exactly. In our experiment, the experimental unit is going to be the subject or the person that is receiving one of the treatments. The factors are going to be caffeine and L-theanine. Those are the 2 factors that we can apply. The treatments are going to be the groups, right? We talked about this. So group 1, 2, 3, and 4 are each representing a unique treatment. The response variable is going to be performance, maybe performance on an exam or something like this. The control group would be group 1 because they are not receiving any of the factors. Is there any blinding? Yes, you could do blinding because you could do a placebo for group 1. And if you wanted to double blind, that would mean that you have to also have the doctors be unaware of which of their patients are receiving placebo or any of the other treatments. And again, possible confounding variables would be anything that could affect the performance. And so just like before, maybe the intelligence or the motivation of a student might also affect performance. And so you might want to do something like a good randomization or maybe a matched pairs design to control and separate out their confounding variables. So in a completely randomized design for this experiment, you could just sort the students alphabetically using a frame and use a random number generator to randomly assign students to groups 1, 2, 3, or 4. In a matched pairs design, which may be even better, but better for your results, but also maybe it's a little bit costly because you have to IQ test the students, and it also takes time. But if you have the time and you have the money, you could IQ test all the students. You could sort students by IQ. You could group students of similar IQ into groups of 4 because we have 4 different treatments, and you can split up the group by putting 1 in each treatment. And this separates out IQ, so it does not act as a confounding variable. And just to emphasize, a completely randomized design is a good design. It's not bad, and especially if you have a large sample size, completely randomized works just fine. But if you have a smaller sample size, maybe it's worthwhile to do a matched pairs design. So pros and cons. Again, a completely randomized design is going to be easier than doing a matched pairs. But as a downside here, if you just have a very small sample size, sometimes confounding variables can sneak up on you and cause an issue. A matched pairs design, as a con, it makes more work for the researcher, but as a upside here is it ensures proper handling of any confounding variables that you're matching up for.